Hi, in this video we're going to be talking about volume. And there are a few different ways of doing volume. There's a method that is covered in the next section but is not part of the AP curriculum. But in this section we'll be talking about disks and washers. So any volume problem I ask you to do can be tackled using some of the principles in this section. And there's one general principle that would work in a variety of contexts, and then what's called the method of disks and the method of washers are just a little more specific, and they're the examples that come up the majority of the time. But there is a deeper principle, and if you understand that, you're good to go. So here's the general principle. Suppose we have a three-dimensional solid. So I'm going to draw some pictures, and don't feel like you have to copy these because I'm going to attempt to draw three-dimensionally. So let's suppose I have some sort of some sort of irregular potato-like thing. Right? So it has a certain roundness to it, but it's not perfectly symmetrical. And now imagine somehow that this is positioned in three-dimensional space so that it's above the x-axis. So here's the x-axis through three-dimensional space. Right, it doesn't really have to be the x-axis, just some axis. And suppose we have a function that gives the cross-sectional area. So for example, maybe if here is like x equals 1, then a of 1 measures the area just of that slice. If I were able to slice through at just what is the two-dimensional slice of this thing corresponding to x equals 1, what would that be? Or maybe here is x equals 4, and there's a slice there, maybe not exactly the same shape. A of 4 would measure the area of that slice. So how could we estimate the total volume of the solid? So what we could do is we could imagine that we break this up into smaller solids. So what I could do is I could take a little delta x here, and I could imagine taking this two-dimensional thing and turning it into something three-dimensional. So think of this as the base, and then I'm building up, but I'm actually building sideways. So I go a little bit here and a little bit here, and then there's kind of like this, right? So it's like I turned something that's perfectly flat into something that has a little bit of a thickness, or sort of imagine this as like a sideways coin. A coin is a three-dimensional thing. It does have some discernible thickness. And I could do the same thing here, right? Here's delta x, move it up a little bit, and we're turning it into something coin-like. Maybe it's not perfectly circular, doesn't have to be. And I could do this repeatedly. Maybe I have another one that looks kind of something like this, right? I'm imagining I'm sort of breaking this up into a bunch of coin-like objects. Maybe I have one here where this is essentially the base, and I go up a little bit, like so. And each one of these things is so how should I put this? There's a general principle that if something has a discernible base and rises vertically, so for example, right, the standard example would be, say, a cylinder. A cylinder has this base that's perfectly circular, and then we go up and we build something on it. And the volume is the area of the base times the height. But even if I had something like a prism, right, this principle works as long as the sides are perfectly vertical. What's the volume here? It's the area of the base, which is length times width times the height. This works for anything. If I have some irregular shape on the bottom, but I'm going up in a way that's perfectly vertical compared to that, the volume would be the area of the base times the height. So each one of these coin-like things would have a volume that's of the form area at some slice times the change in x. Right? This is the volume of one of these coins, for lack of a better term. And then I add them all up. So this would be my volume estimate. It's just an estimate because I've taken some of the curvature out of this. This would not have curved sides, it would have a sequence of straight sides. But it would be a decent volume. Right, so that's how we could estimate this thing. Well, hey, it looks like a Riemann sum, a value of a function times some sort of width or thickness, and then I add those all up. What turns this estimate into the true answer? A limit. And the limit of a Riemann sum is an integral. So we'll notice that this is a Riemann sum, and it would be more accurate if we take more tinier slices. So the true volume comes from taking a limit, and it's this. Where here the idea is x equals a is the x value where this thing starts, and x equals b would be the x value where this thing ends. So if we know the function that measures the area of each slice, and that's not necessarily easy, but if we have a function that measures how thick is it at each thing, we integrate. This is actually the two-dimensional analog of what we did with one dimensions. The way we figured out an area was by integrating f, but f is just measuring height. So essentially, if you integrate the height function, you get area. So integration turns a one-dimensional quantity into a two-dimensional quantity. Well, if you integrate area, assuming you set this up the right way, that gives you volume. So here's an example. See if you can make sense of this. Consider the region R below y equals sine of x and above the x-axis from x equals 0 to x equals 3. You should be able to draw a rough picture of this. I will do it in a moment, but you just need a schematic to organize things. We're going to think of R as the base of a solid, and each cross section perpendicular to the x-axis is a square. Using your calculator, find the volume of this solid. So hit pause and at least try this. Okay, so here we go. Here's y, here's x. Here's pi, here's 1. The graph of sine would do something like so. So R is that region. And we're going to think of this as the base of a three-dimensional solid. So actually think of your piece of paper or your screen as the bottom, and imagine that we have something coming up from that. That this thing in green is the bottom of something. And it says each cross-section perpendicular to the x-axis is a square. So if here's some value of x, think that that is one side of the square, and I'm going to try to draw this to give the illusion of three-dimensionality. But imagine this coming up, right? So you're going to have to imagine this in your mind's eye. I'm attempting to draw something three-dimensional in 2 dimensions, but it's literally coming straight up. That this segment right here is the base of a square, and the square is coming up. Right? There would be a different square. Maybe if this is x3, this would be the base of a different square. Imagine it coming straight up. Right? I'll try to draw that. And if we took all of these together, we would get a three-dimensional thing. It's very hard to visualize what this whole thing looks like. The good news is you don't have to visualize it perfectly. If you understand what the slices look like, you don't necessarily have to struggle with the fact that complete visualization is hard. If one slice at a time you can visualize a square, you're good to go. So we're going to use this principle. To find volume, we just integrate whatever function gives us the area of each slice. And we'll notice we're trying to find the area of a square. Area of a square is side squared. But what is the side? The side is this distance. It's literally the height from 0 up to y equals sine of x. So our volume would be the definite integral from 0 to pi of sine of x squared dx. And this can be done by hand if you are clever and know the right tricks and remember some trig identities, but I just said use your calculator. Right? For a lot of these problems, doing the whole thing by hand is a little too much, but that's okay. You're not required to. The hard part here is understanding what integral are we supposed to do, and then assuming you have some basic facility with your calculator, you can make the calculator do the rest. So I am putting things into my calculator simulator right now. Make sure you are in radian mode. And I get this to 3 decimal places is 1.571. What you might notice is that this is a decimal approximation of pi over 2. So if you are clever and do this by hand, the specific number pi over 2 will emerge. But for our purposes, we just want to understand what integral does this, and we'll leave it to technology to give us a very good estimate. So I want you to know that principle, right? If you have an area function, you just integrate it, and that applies in a lot of different ways. But most common applications come from things that are round. Out there in life, a lot of things we deal with in one dimension are round or circular. And those are called solids of revolution. So these are created when we spin something around a line. So this is a hard thing for me to show just through a video, but imagine you take some object and you spin it around a line, and you look at what is the path carved out, right? Imagine holding one finger in front of you, hold a finger horizontally, then take your other finger, put it above that finger, and spin it around your first finger. What's the path of your fingertip? The path of your fingertip is a circle. What's the path of your entire finger? The path of your entire finger is a cylinder. When we spin things around, we get things that are essentially round. So we can get cones and spheres and cylinders, things that are round but irregular, like a flower vase or a drinking glass, right? We can get all kinds of round things. They have radial symmetry. So let's look at an example here. Similar example. Let R be the previous region, and suppose we revolve R about the x-axis. So I'm going to draw my picture down here. So R is the same thing. Oops. What is the principle? So imagine we're spinning this around. So hopefully you can imagine if in 3 dimensions you spin this around the x-axis, you'll get something that's sort of football-ish, kind of, or rugby ball-ish, right? It'll be round but not spherical. It'll feel like it narrows kind of quickly at the ends. How do we find the volume? We figure out what is the function that measures the area of each slice. So what I recommend is pick just some sort of generic x along the way and try to visualize what is the slice corresponding to that value of x. So we can take the vertical part of the region R corresponding to x and just imagine what is created when we spin that vertical segment around. Hopefully you can imagine that when we spin that vertical segment around, we get this circular disk. So sort of in math speak, the circle is just the outside while the disk is the outside as well as everything inside. So this disk is the slice of the football kind of shaped thing at this x value. It's round, it's circular. So how do we find its area? Well, the area would be pi r squared. But what's the radius of this circle? The radius of this circle, here we are at y equals 0. That's one end of that radius. Here we are at y equals sine of x. That's the other end. So the radius of that circle is sine of x, regardless of what x is. If I drew this somewhere else, the radius over here would be sine of this x coordinate. So we have pi times sine of x squared. So what would our volume be? It's a definite integral. This thing starts at x equals 0 and ends at pi. And the area of each slice is pi times sine of x squared. And you could put that in your calculator, or you could notice that it's the integral we did before, but multiplied by pi. So this would be pi squared over 2. Or you could get a decimal in that. In the short term, I'm much more interested in you learning which integral are you supposed to do for these volume problems than pausing to do each specific integral. Either you do it on your calculator, and you should know how to do that, or you have to roll up your sleeves and do it by hand, but we're not going to dwell on that right now. Right, so this is called the disk method. It's when we realize that every slice is a disk. So the area formula that we're integrating looks like the area of a circle, pi times something squared, where that radius somehow comes from the graph. In this case, it's literally just what is the function value. All right, let's try another one. Let S be the region below y equals 4 and above y equals x squared. So let's draw a quick picture. And your pictures can just be schematics. They don't have to be super accurate. We just want to be able to organize the information. So y equals 4 is a horizontal line. Y equals x squared is our standard parabola. And S is this region. Hopefully we realize intuitively that those corners are at -2 and 2. Now, suppose we revolve this region about the horizontal line y equals 4. What's the volume? So again, think about a slice, a general slice. Here's some value of x. Here's the part of the region corresponding to x. And we're going to spin it around y equals 4. So when we spin that around, we get a disk that looks like this. There's our disk. There's the center of the circle, and this is our radius. So the area of the slice is pi r squared, because each slice is a disk. But what is that radius? That radius would be the distance between this point and this point. At that top point, y equals 4. At that bottom point, y equals x squared. So we just subtract. And I've said this before, but if you're measuring a vertical distance, top minus bottom, end of story. Don't worry about whether something is positive or negative, you're going to blow it. It's top minus bottom. So our radius here is top minus bottom, which means our area formula is pi times 4 minus x squared squared. So our volume formula, we would be doing our volume from -2 to 2, because that's where our region begins and ends. And the area of each slice, it's a disk, pi r squared, where the radius is 4 minus x squared. So it's not just x squared. It's not always as easy as, oh, the radius is the function. You have to visualize where is your disk, where is the center of your disk, where is the edge of the disk, and how far away are they? Dx. And just as a quick review, I will say this one is doable by hand. If you were to do it by hand, you would have to, well, let's put that pi in front. Pi is just a constant, so we can get that out of the way. And then if you FOIL out the other part, you would have 16 minus 8x squared plus x to the 4th dx. So this is doable by hand, but a bit tedious. So I'll just say steps. And then finally you get an answer. Again, for the purposes of this video lecture, I'm more interested in just understanding how we set these problems up, and then you can finish them later. You can punch this in your calculator, or if you want a good exercise, punch it in your calculator, do it by hand, and see if your answers agree. Remember the pi. So as I've said before, these two examples used what's called the disk method. because each cross-sectional slice was a disk. Now, sometimes our revolution creates a solid with a hole in the middle. Disks don't have holes in the middle, but sometimes do. And if you have something round but with a hole in the middle, that's called a washer. So this is washer in the sense of not like the machine that washes clothes, but those little metal things that sometimes are put on screws or bolts to separate the pieces. So a washer would be this region. It's basically a disk with a disk removed. And when we have a washer, we usually want to think, okay, there's this big radius from the center to the outside. And then there's this smaller radius from the center to the inner circle. And the area of a washer would be the area of the big circle minus the area of the small circle. If you want to factor out that pi, you're welcome to. So it's big radius squared minus small radius squared. And let me be very clear that it is something squared minus something squared. This is not the same as radius minus radius squared. There are problems where this is the relevant calculation. This is more likely to come up in a disk method problem, but be really careful what you're doing. The volume of a washer is an area formula minus an area formula. Pi times a radius squared minus pi times a radius squared. If you want to factor out the pi, that's great. So when we do a washer problem, our integral looks like this, where the big R and little r are dictated by the details of our problem. They'll probably involve some sort of function that's mentioned in the problem, but we will need to be careful about the details. Right, so the trick is to correctly measure those radii. So let's look at an example. So let R be the region from x equals 0 to x equals 2 below y equals 2x and above y equals x squared. So let's try to draw a picture of that. So y equals 2x looks something like so. Here's 2. Here's the point 2 comma 4. Y equals x squared is our standard parabola. Conveniently, it also goes through 2 comma 4. And R is the region between those two below the line and above the parabola. So R is this rather slim thing. That's R. And we're going to revolve that about the x-axis. So imagine taking this green thing and spinning it around the x-axis. Write an integral for the volume of the resulting solid. You'll notice I didn't even ask you to evaluate. I just want to see what it looks like. So here's the idea. Imagine some value of x between 0 and 2. Think of the vertical section of the region corresponding to that. What does it look like if we take this blue vertical segment and spin it around the x-axis? You have to imagine this. It's a three-dimensional visualization. I can't show it to you in this video. But you'll see it's a washer. We'll get something round, but there's this hole in the middle. All of this stuff is not part of what we get. So each slice would look something like this, right? This part spins around, so we get all of this. So we need to know our two radii. There's the little radius, and there's the big radius. Right here is the center of the circle. So our little radius is this distance. From here to here is basically measuring from the center of the washer to this inner edge. While our big radius is this distance. And both of those distances are just the distance from y equals 0 to one of those graphs. It's a little inconvenient that R is the name of this particular region and the abbreviation I often use for radius. I apologize for that confusion. So I'm just going to erase this. The region doesn't really need a name. So our outer radius is from 0 up to y equals 2x, so that's 2x. Our inner radius is from 0 up to x squared, so that's x squared. So the area of each slice would be pi times the outer radius squared minus pi times the inner radius squared. So what's our volume? It's the definite integral from 0 to 2, because those are the beginning and ending x values, of pi, I'm going to factor out the pi, times 2x quantity squared minus x squared quantity squared. There's no need to do anything else. I would actually recommend leaving it like this. Yes, I know how to square those, but writing it this way makes it really clear where everything came from. And this is something that shows up on the free response section of the AP. They will ask you simply to write the integral expression, but not to evaluate it. Maybe they know your time is limited. Maybe they know it's something that's ridiculously hard to do without the calculator. They're just testing conceptually, do you know which integral is relevant? So you don't have to do any evaluation, but you have to present something that is correct. If there's a parenthesis error, they are not going to play this game where they decide what you meant. They will read what you wrote down. And, so for example, if these parentheses are missing, that's a problem. 2x squared is not the same as quantity 2x squared. All right, let's look at another one. Suppose R is the same region above. Now, what if we revolve it about the horizontal line y equals 5? What would that be? So I'm going to redraw the picture just for simplicity. I'm going to draw it a little bit bigger. So here's y equals 2x. And here's our parabola. Here's our region. And now, what if we revolve this around y equals 5? So as before, imagine some x and think about the portion of the region corresponding to that x value. We're going to spin it around this horizontal line. So we want to think that this point right here is going to be the center of the circle. This point right here is basically going to be the inner rim. And this point right here is going to be the outer edge. So hopefully you can visualize when we spin this around, we are going to get a washer. We're going to get this round thing with this point at the very middle. This will be the inside of the washer. This will be the outside of the washer. So our big radius would be this distance. From the center to the outer rim, outer edge would be our big radius. Our small radius would be to the inner rim. So our big radius, well, the y-coordinate here is 5. The y-coordinate here is x squared. How far apart are they? Top minus bottom is 5 minus x squared. Inner distance, inner radius. Center here is at 5. This is at 2x. So from a y-coordinate of 5 to a y-coordinate at 2x, top minus bottom measures that distance. So the area of each slice would be pi times outer radius squared minus inner radius squared. And our volume would be the definite integral from 0 to 2 of that area formula. Be super careful about parentheses and grouping symbols. The radius itself involves subtraction. The radius itself involves subtraction. And then there's this extra layer of subtraction because of how washers work. This is a problem where you would hope you're allowed to do your calculator. It's all polynomials in here. Like, you can do this, it's just algebra, but there are a lot of opportunities to mess something up. Okay, our examples so far have involved integrals in x with vertical cross sections, but the principle works if we change the orientation. If we have a solid that's round in a horizontal fashion, it might make sense to measure the area at each y and integrate those. So let's look at an example. Consider the region bounded by y equals the square root of x, y equals 3, and the x-axis, and the y-axis. So y equals 3 is this horizontal line. Y equals the square root of x, looks something like so. Just a schematic, doesn't have to be perfect. This intersection happens at the point 9, 3. It's not quite to scale, who cares? And we're looking at the region bounded by the square root graph, y equals 3 on the y-axis, this region. Now, what if we revolve this region horizontally about the y-axis? So try to imagine that here, this is the axis, and we're spinning this thing around, right? So after we spin it around, it would look something like so. Right, I will attempt to give a sense of the three-dimensionality of this thing. Sort of funnel-shaped, but without straight sides. Right, we spin this around horizontally, and it looks something like so. So the roundness happens horizontally. So we might think, oh, horizontally, all of the horizontal slices look like discs. So the best way to figure this out is to say, oh, if I measure by y coordinates, at this y coordinate, if I adjust for height, at a given height, I have a disk. And that area of a disk is really easy to figure out. So here, x is equal to 0. Here, I have the point where y equals the square root of x. So x would be y squared. So here, my x coordinate is y squared. So this horizontal distance would be x coordinate over here, which is the square of whatever y is, minus x coordinate here, which is 0. So this radius is horizontal distance, right minus left would be y squared minus 0, so that's y squared. So the area of each horizontal disk is pi times y squared squared. We're measuring it at y. We could pick a different y value here, y2, and get a different radius and figure that out. Y is changing, and we can measure the area of each horizontal disk as a function of y. But the principle is the same. We have this axis running through our three-dimensional figure. We have an area function that measures the area of each slice, so we just integrate that. So here y starts at 0 and ends at 3, and the area of each slice as a function of y is pi times y squared squared, dy. Make sure you write this correctly. If this were a problem on the AP, or a problem that I give you, you might not get full credit if your differential is wrong. Let's do this one. This one's not so bad. So this is the definite integral from 0 to 3 of pi y to the 4th dy. So our antiderivative is pi over 5 y to the 5th from 0 to 3. 3 to the 5th is 243. 0 gives us 0. So we have 243 pi over 5. That is our exact answer. You could put that in your calculator for an estimate. Okay, so there's a lot to digest here. I'm sure you haven't mastered it right away. This is the kind of thing you should practice in class, in small groups, talk to each other, talk to me. This is a hard thing to learn without physically being there to see things moving in 3 dimensions, so ask questions as necessary. But that's the